Hi, my name is Savannah Harris, and this is my Lab 5 Find Your Own Adventure presentation. For this lab, I decided to take on Felix Baumgartner's Stratus Jump. For this particular example, there aren't any videos that capture the motion in a way that Tracker would be useful, but Red Bull did publish the data that can be seen here. As you can see, the data leads up right to the point before Felix pulls his parachute and is split up into 4 sections. For my code, I also split the jump up into different sections that mirror these 4 sections described. In my calculations and in my code, I use Newton's second law, gravitational force, and drag force to calculate for the unknown constant drag force B. Here you can see some of the basic setup of my code, such as the mass of Felix and his gear and also his initial position, which was found online. It was also assumed that he fell from rest and therefore his initial velocity would be 0. This is the code for the first section of Felix's fall, where he is getting up to the speed of sound. 2 things here to note that are important are that the B constant was found by trial and error to be 1.2, and also that the G is not just 9.8 since we were falling from very high above the Earth's surface, but it actually changes depending on the ball's position. This same format was followed for the other sections of Felix's fall. It is important to note that while F net does equal F weight plus F drag, F weight and F drag are not constant throughout Felix's fall, and therefore they need to be calculated within the while loop so that way they are recalculated at every step because weight is dependent upon Felix's position above Earth and drag is dependent upon his velocity. Due to time constraints and an inability to find the necessary constants, I'm going to focus on the first 2 sections until he reaches maximum speed for my analysis. Here you can see the comparison of my model and reality. I believe the margins of error are high for the final position because I chose the wrong height given by the website since the percent error hovers around the same number. The final position data found here was not listed with a starting height, and therefore I believe it is possible I chose the wrong height should drop from since a range was listed on a different tab within the website. However, my margins of error for part 1 and 2 for final velocity as he reaches 1.25 Mach are very small, and therefore I have confidence in the drag force constant B. After the first 2 sections, because the drag constant is changing, you will notice that my model deviates further from the truth as I go on in my program. But because I was unable to find the information necessary to model a time-dependent drag coefficient, this is how my model stands, and I am only accurate for the first 2 sections of the jump. Here is my y position versus time graph for the model. Just a note here, you don't see the increase in slope during the first portion because he accelerates very quickly and the scale of the graph doesn't really allow you to see the increase in slope very well. But as you can see, there are 4 distinct portions of where the graph has a different slope or different rate of change of slope, which correspond with each of the different sections of Felix's fall, each having a different drag force. Using the data on the Red Bull website, I was able to build a model that showed Felix's fall from the stratosphere. The fall was modeled in 4 stages, each having a different drag force constant. This change in drag force constant is caused by a multitude of factors including Felix's body position and the air density, which depends on his altitude. These constants were used finding trial and error to get the lowest margin of error. As Felix falls from his high altitude starting point, the air around him gets warmer. As he falls to lower altitudes, the air becomes more dense and has more air molecules per cubic meter, and therefore holds heat better than the air of a higher altitude. This changes my predictions because the more dense the air, the greater the drag force constant is going to be. This means that Felix will experience more drag at lower altitudes than he did at higher altitudes. This needs to be taken account for in the code by raising the B value slightly in order to compensate for the warmer, denser air that provides more air resistance to Felix as he falls. However, it is important to note that the increasing B in each section is not only due to the change in the air density and temperature, it also has to do with the position that Felix is in. So for instance, he starts in delta position where his head is down, where he's trying to gain as much speed as possible, as quickly as possible, and then he moves positions to be in the standard skydiving position with his arms and legs out in order to create more air resistance to slow down, so that way he can pull his chute at a safe velocity.